When I was little, I always wanted to have my own fairy dust. But what if I wanted to make my own fairy dust now? You would need some silver or gold. Then I would grind it down into very, very fine bits, and then I could do whatever I wanted with it, right? But if I looked down at my fairy dust, would it look gold or silver? It wouldn't. In fact, if I could change a few parameters, I could make it any color I wanted it to be. Thanks to Localized Surface Plasmon Resonance. You may have learned from your high school chemistry class that an atom is the smallest unit of an element that retains the physical properties of that element. While this is true, not all properties are maintained. Once you get down to chunks only hundreds of thousands of atoms large, at a scale where things are measured in billions of meters, things start to get very weird very fast. Take the element gold, for example. It is the third most conductive element. It is also extremely malleable and ductile. An ordinary piece of gold, also called bulk gold, behaves in the way you would expect it to, by absorbing all incident wavelengths of light except for the ones that result in yellow light. How this works will be answered in a minute. But what happens when gold nanoparticles are exposed to light? To find out, we need to get
really smart.
Imagine that this is an electron microscope and we are able to see a single gold nanoparticle. Here is a magnified view of the same nanoparticle. Of course, it is not to scale, for there would be many more atoms. The nucleus of one of the atoms has been labeled, and the others are marked with Au, the atomic symbol for gold. The atoms in a metal, nanoparticle or not, are always surrounded by a sea of free-flowing electrons. This sea of electrons is much like a real sea, flowing around atoms which could be portrayed as anchored buoys. And just like a real sea, this one has waves. We'll get back to that wavy stuff in a minute. To really figure out what happens to metal nanoparticles when exposed to light, we need to look at another wave, a light wave. The anatomy of a light wave is at the heart of this discussion. You see, light is actually two waves inseparably tied together.
Aww.
One, an electric field, and the other, a magnetic field. Together, they become an electromagnetic wave. Alright, we're back from that little detour on light waves. Now, we can look at the whole picture and figure out how localized surface plasmon resonance works. I've drawn another nanoparticle along with its sea of electrons. The sea of electrons oscillates with a certain frequency depending on the shape and size of the particle, creating an electric field that resonates with certain wavelengths of light, thus changing the color of incoming light while it's being reflected. This isolated electric field in a nanoparticle is called a plasmon. The diagram shows the electric field's portion of light's electromagnetic wave being influenced by the resonance of the electrons in the plasmon. At these sizes, the size of the nanoparticle, ergo the plasmon, is close to that of visible light, and can thus change its wavelength. This is the reason why bulk gold doesn't change color, yet nanogold can. There are many applications for LSPR. Gold nanoparticles in LSPR may not be used for fairy dust, but they're definitely very important.